morning. My name is Georges Meylan from EPFL in Lausanne. I'm in charge of the prize selection committee of the EAS, and today I'll chair the first part of this session related to the MERAC prizes. I remind everybody to not hesitate in nominating as many good people as you have for any of the EAS prizes, the Tycho Brahe, the Fritz Zwicky, and of course the MERAC prizes. And we'll start today with the first prize, the Theoretical Astrophysics MERAC prizes, which has been awarded this year to Aris Tritsis, who was in Greece for his PhD thesis, and he is now in Canberra in Australia. And the reason was for fundamental contribution to the physics of the interstellar medium of the process of star formation. Aris, you have the floor.
All right, can you all see my screen?
Perfect, you can start.
Perfect. All right, so hello everyone. First off, let me start by saying that I sincerely hope that you and your families are well and unaffected by the coronavirus situation. Before we begin, I would also like to say a very big thank you to the European Astronomical Society and the MERAC Foundation for this very special honor, and thank my PhD supervisor, Kostas Stasis, as well as the entire Department of Physics at the University of Crete for the continuous help and support throughout my PhD and to this day. And now, in this talk, I'm going to present part of the work that I did during my PhD and how this work brought me to the project that I'm currently working on, which I have named HOMERIC. So HOMERIC stands for Helios Magnetic Field as evident from stRiated interstellar clouds. And with this project, I aim to create a three-dimensional map, a three-dimensional atlas of the strength and the orientation of the mean component of the magnetic field in the galaxy. But before I go into the science, I first feel obliged to explain the acronym, for which I'm particularly proud of for two reasons. The first very modest reason is that according to the Oxford Dictionary, HOMERIC stands for epic and large scale. And the second reason why I like this acronym so much is that the word HOMERIC comes from the name of the ancient poet Homer, who wrote the Odyssey. And much like the journey of Ulysses to Ithaca, which is a small island in Greece and my hometown, finding the galactic magnetic field has been a real odyssey. Now, moving on to the science, I left something here that I didn't explain. I didn't explain what are striated interstellar clouds, or in other words, what are striations. So striations are these faint, ordered, hair-like structures which we see in the outskirts of molecular clouds. So in this slide on the left, I show an image of a molecular cloud, and the dense region here is surrounded by this network of striations, which are marked with the cyan arrows. But striations do not just appear in molecular clouds. They are in fact very common throughout the interstellar medium of the galaxy. And the figure on the right in the slide is an all-sky atomic hydrogen map. And as you can see, away from the galactic disk, most of the clouds appear to be striated. And striations have this amazing property that wherever they are observed, they always seem to be aligned with the magnetic field. So in this slide on the left, I show a region with striations from a molecular cloud. And the black segments here are optical polarization measurements showing the direction of the magnetic field. And as you can see, even by eye, striations follow the magnetic field very well. And the figure on the right is exactly the same thing, now quantified for another molecular cloud. So this is the distribution of the relative orientation between the magnetic field and striations. And as you can see, there is this peak at very small angles, indicating again the preference for alignment. And despite the fact that striations are very common throughout the interstellar medium, their formation lacked explanation for almost a decade after their discovery. So during my PhD, I performed a number of numerical experiments, testing out various formation mechanisms that could potentially have accounted for the formation of striations. And in this particular slide, I show the setup of my simulations for just one of these scenarios that I tested. And in this case, in this scenario, striations are formed as a result of fast magnetosonic waves. So on the right in the slide, I show an animation of the magnetic pressure in the simulation. And what is essentially happening here is that you have two magnetic field lines approaching each other, dragging the gas with them, creating compressions in the gas. And vice versa, when the same two magnetic field lines move away from each other, dragging the gas with them, they create rarefractions or underdensity in the gas. And having a spectrum of these waves with different wave numbers creates a complex pattern of overdensities and underdensities in the gas, which we end up seeing as striations. And in fact, these compressible fast magnetosonic waves can be excited through nonlinear interactions with Alfvén waves, which I show here on the left. So in this slide, I show the results from my simulations on the right. So this is a density snapshot along with observations on the left. And in order to quantify the results from my simulations, I also measured the mean contrast between adjacent striations. So for the parameter space that I examined, I found a value of 5 to 10% in the simulations, as opposed to 10 to 20% in the observations. So just for reference, for every other scenario that I tested that could have potentially accounted for the formation of striations, the mean contrast was no more than 10 to the minus 3%. And as a result, this model of fast magnetosonic waves stood out as the only one being able to explain their observed properties. And having such a model that can explain the observed properties of the structures is really important, is significant, but what's even more important is to actually use this model to make detailed predictions. And the first prediction that arose from my model for striations is that when you have waves and you have boundaries, these waves can get trapped and you can get normal modes. So in this slide on the left, I show a cartoon representation of a cloud with red cylinders representing striations, and the black arrows represent magnetic field lines, which assume to be along the Z direction. So for this sort of box-like cloud, the wave numbers of the normal modes will be given by the equation here on the right, where N and M are integers ranging from 0 to infinity, and Lx and Ly are the dimensions of the cloud perpendicular to the magnetic field. So I went ahead and attested my prediction towards the Musca molecular cloud, which is an isolated cloud in the southern hemisphere. And this is a really important cloud for two reasons. The first reason is that Musca is not actively forming stars yet. And as a result, by studying Musca, we can study the initial conditions for star formation. And the second reason why this is an important cloud is because of its elongated morphology as projected on the plane of the sky. People have always speculated that this is an interstellar filament. This was supposed to be the best example of a cylindrical-like cloud we can find in nature. So going back to my prediction of normal modes, I took cuts perpendicular to the long axis of striations inside this green box shown over here, and I computed the power spectra of these cuts, which you can see here on the left. So in this power spectra, I also identified the peaks, which are marked with the red dots, and I plotted these peaks as the black distribution shown on the right. So what this black distribution shows is the number of peaks at different wave numbers. Next, what I did is that I considered the value for the wave number in the first peak in the distribution, so that's the first red line. And in the equation on the upper right, I set n equals to 1, m equals to 0, and I found a value for Lx, which represents the length of the cloud on the plane of the sky. And then I repeated the exact same process, but for the second peak in the distribution, so that's the second red line. And this time I set n equals to 0, m equals to 1, and I found a value for Ly, which represents the depth of the cloud along the line of sight. Finally, I put the values for Lx and Ly back into that equation, and for different values of the integers n and m, I predicted analytically the wave numbers that should have been present if normal modes were indeed established in this cloud. So these analytical predictions are shown with the blue dashed lines, and as you can see, they fall right on top of the observations, so I was confident that normal modes are indeed established in this cloud, and that the values that I measured for Lx, the length, and Ly, the depth of the cloud, were accurate. And the final thing to notice from this slide is that the values for Lx and Ly are in fact comparable. So what this means is that Musca, which was once considered to be the prototypical filament, is in fact a seed-like structure, a pancake which we see edge on. So this was the first time that normal modes were ever observed in a molecular cloud as a whole, and the first time that we were able to accurately determine the three-dimensional structure of a cloud. Finally, we also converted the wave numbers, the spatial frequencies, into sound. So the movie in the next slide is the Song of Musca. Please enjoy. right? So this was a spectacular result, but in fact, the prediction for normal modes was not the only one. There was in fact a second prediction, which I think is even more important. So if we linearize the image equations, then we can arrive in these three expressions for the perturbed velocity, the perturbed column density, the perturbed magnetic field, because of the waves creating striations. And the first thing to notice here is that the exponential part right at the end is the same in all these three equations. So what this means is that if I were to take cuts perpendicular to the long axis of striations, then the power spectra of velocity, column density, and magnetic field should all peak at the same wave numbers. And the second thing to notice is that in the perturbed velocity, we have the amplitude of the waves appearing, so that's A and E, as well as their frequency, that's omega and E. And in the perturbed column density, we have again the amplitude of the waves, their wave numbers, K and E, and the mean column density, which is denoted here as NH0. So if I further take the ratio of powers in the power spectra between velocity and column density, then the amplitude of the waves cancels out, and all I'm left with is that the ratio of powers equals omega over K over the mean column density. But from the dispersion relation of fast magnetosonic waves, we know that omega over K is approximately equal to the Alfvén speed. And if I further substitute the expression for the Alfvén speed, then I can arrive in this equation shown on the bottom right, which is a new analytically derived method for measuring the strength of the mean component of the magnetic field, and everything on the right-hand side of this equation are in fact observables. So by utilizing observations of striations, we have a new analytically derived method for measuring the strength of the magnetic field. And of course, I tested this analytical method with numerical simulations considering molecular cloud conditions. And the simulations also had non-equilibrium chemical modeling with a very extended network of 300 species and 14,000 reactions. And I also post-processed my results with a non-local thermodynamic equilibrium, multi-level, three-dimensional linear data transfer code that I developed called PIRET. So on the left in the slide, I show some of the results from the simulations. So the red lines are the power spectra of velocity cuts perpendicular striations. The black lines are the power spectra of column density cuts perpendicular striations. And from this set of power spectra, I was able to correctly retrieve the value of the magnetic field initially in the simulations. But what interests me more these days is actually the application of this method to H1 observations, and this also brings me back to HOMERIC. So on the left in the slide, I show again the power spectra of velocity with red and column density with black. And as predicted analytically, the power spectra peak nicely at the same wave numbers. And what is more, the variation in power in the velocity and the column density is similar. So from this power spectra, I can arrive in the plot shown on the right, which shows the frequency of the waves omega as a function of their wave number, and what is essentially an observational derivation of the dispersion relation of fast magnetosonic waves. So if I find this relation for striations in a cloud, then my model is ipso facto verified. And from the slope of this relation in linear scale, I can find the Alfvén speed, and in turn, I can find the value of the magnetic field. And vice versa, if the structures in a cloud do not obey this relation, then I cannot say anything regarding their formation, nor can I measure the magnetic field. And this is really important because this way I avoid false positives. So this method can only be applied where its assumptions hold. But in fact, in this slide, I show the results from just one cloud, whereas I have applied this method to two clouds located along the same line of sight and perform magnetic field tomography. And this is exactly what I show in this slide with the locations of the clouds in the galaxy. And what's interesting here is that the values that I found for the magnetic field, so that's 20 and 50 microgauss, were a factor of 3 to 5 higher than what galactic magnetic field models predict. And now that I have the proof of concept established, I figured to myself, why not do this for the entire sky? So the first step in applying this method to the entire sky is to actually identify individual clouds and striations within these clouds in individual lines of sight. And to this end, I have developed an automated algorithm to perform a Gaussian decomposition of all spectra in position-position velocity data cubes. So on the right in the slide, I show an integrated position-position velocity data cube, and each pixel here contains a spectrum with 4 examples shown with the black lines on the left. And the red lines here are all the components that I have identified in my Gaussian decomposition added up together. And as you can see, they fit the observed spectra really well. So once I have identified all of my components, then for every component, I can go ahead and I can calculate its velocity map, its first moment map, its column density map, and a map that entails the orientation of structures that are evident in the column density. And this is exactly what I show in this slide. This is just an example for just one of the components that I have identified, with the velocity on the left, the column density in the middle, and the orientation map on the right. So from these three maps for every component, I can then compute average values, and I can plot all of my components in the three-dimensional space of average orientation, average velocity, and average column density. So each point here is computed from the three maps and similar to the three maps shown in the previous slide. So once I have this plot, then I can utilize a clustering algorithm to cluster my components back now into individual clouds. For this particular region, I have identified 4 clouds, the individual components of which are shown with the different colors. And the distance to each cloud will be given by 3D dust reddening maps. So the end result from all of this will be the creation of a three-dimensional map of H1 clouds in the galaxy. And once I have this map, then I can go ahead and I can find striations within individual clouds now. I can measure the orientation and thus measure the orientation of the magnetic field, since the two are always aligned. And I can apply my method to measure the strength of the magnetic field. So this way, I will create a three-dimensional map, a three-dimensional atlas of the strength and the orientation of the plane of sky component in the galaxy. And as I'm sure you know, having these two maps would be really important for a number of areas within astrophysics and cosmology, including ultra-high energy cosmic ray propagation studies, the removal of galactic foregrounds to CMB polarization experiments, and the list goes on and on. So precisely because of the importance of these questions, I really do think that the goal of creating a three-dimensional atlas of the strength and the orientation of the magnetic field in the galaxy is a really worthwhile one, is a journey worth taking, and with HOMERIC, I'm here to achieve this. So thank you very much for your attention.
Thank you very much for these very interesting talks. Sara, I do not see any question. However, some other people have problems, and I received a question from Lucio Mayer, who is a member of the board of the MERAC Foundation. So I'm going to start with him, and then I'll give maybe the opportunity to Sara to ask other questions if we still have time. So first question, turbulence would affect the propagation of MHD waves and generically blur sharp boundaries. How is turbulence accounted for in the models? Is that just self-generated as MHD turbulence, or is that generated also by other mechanisms like supernova explosion or gravito turbulence?
So specifically for Musca, there is no supernova explosions nearby. A number of simulations have shown that striations only appear in subalvenic turbulence. And in fact, subalvenic turbulence with a superposition of MHD waves is basically indistinguishable, and a superposition of MHD waves is what I've been talking about all this time. So in the simulations, we only have MHD waves.
Okay. And another question, does the presence of normal modes, which clearly are not damped, allow to place constraints on the degree and nature of turbulence?
I haven't actually thought of that. But again, in the picture of Musca, the cloud is collapsing along magnetic field lines with MHD waves propagating in the direction perpendicular to the magnetic field. And in fact, I'm not sure, to be a bit provocative, I'm not sure if turbulence is in fact important for Musca. Line observations, spectral observations have shown that Musca is not turbulent. It is in fact a sonic-like structure. So yes.
Thank you. So Sara, do you hear me?
Yes, you don't see the questions? I'm putting questions to you. Oh, sorry. So can I ask the questions?
Yes, read them, please.
Okay, maybe mute yourself, Georgia. There's a lot of echo. Let's see. Okay. So a question that comes from Ciro Pinto. He says, brilliant idea about the pancakes. I suppose that statistically some should be observed face on and appear much broader. Are you aware of any examples in a galaxy?
So there are some examples of clouds which are supposed to be seen as illuminated from cosmic rays. But I think that if they were seen face on, then it would be much harder for us to notice them, because the column density would be smaller.
All right. Another question that comes from Marco Dart. How will future missions, such as, for example, JWST or SPICA, can help in the study of star-forming regions and turbulence?
So I think HOMERIC is really connected with SPICA and other future missions, including PACIFY. The advantage here is that, compared to SPICA, is that I can do this. I can measure the magnetic field in a tomographic like manner. So I won't just measure the integrated polarization, but the two are definitely complementary.
All right, we have another question from Alvaro Sanchez Monge. He actually says he has a couple of questions related to the Gaussian fit of the spectral H1 features.
Yes.
First, how do you deal with the absorption features in the H1 lines?
I don't have a good answer to that yet. So this is all preliminary.
Second question, how do you assign which velocity component is related to each other velocity component in another pixel?
So this is why I do the clustering. So I find all of my components, and then it's not enough to just measure clouds in just velocity. That's why I find the orientation of the column density, so that I can cluster components to clouds. So I don't do that. I let the clustering algorithm tell me how many clouds are there.
There are no more questions.
Sorry, I can't hear you.
Unmute, okay. I think you hear me now. Is it right?
Yes.
Yes. Okay. So no more questions. Aris, thank you very much. Going straight to the next speaker, who is Jorryt Matthee, MERAC Prize for Observational Astrophysics. Oh là là. Pascal. Je me suis fait kicked out.
Everything is working.
Is it working? Okay,
Yes.
so I do not see anything anymore, but I'll go forward. Thank you very much for your patience, and sorry for this incident. So Jorryt Matthee, he's receiving the MERAC Prize for Observational Astrophysics, with the reason related to spectacular results that have transformed the way we see and understand distant galaxies across time. And Jorryt did his PhD thesis in Leiden, but he's now in Zurich at the ETH. And please, Jorryt, you have the floor for the next half hour or so. Thank you.
All right, let me share the screen.
Ah, yeah. I also recovered a lot of capabilities with my screen. Thank you.
All right. Yeah, it's really a great honor to be here in my living room to give this talk to all of you. In these 20 minutes or so, I'll be presenting some highlights from the work that I've been doing as part of my PhD thesis, which is titled Identifying the Origins of Galaxy Formation. As you just heard, I did that PhD in Leiden in the Netherlands. So, but really, before starting on these highlights, I want to remember everyone that and say a big thanks to all my collaborators. So I wrote this thesis. You can see the book cover here, but I had many co-authors who helped on several aspects of this work. So I want to thank them on this occasion. In particular, I want to thank my supervisors, Huub Rutgering, Joop Shea, and in particular, my daily supervisor, David Sobral from the University of Lancaster, who really supervised me by day and sometimes by night And I really want to thank him for all the fun we had in undertaking all these surveys, starting from small telescopes and finally observing galaxies with the most recent new instruments that I'll show in this talk. I also want to thank the observatory in Leiden for allowing me to do a PhD through a Huygens Fellowship, which allowed me to do several distinct research topics simultaneously with multiple supervisors that you can see here. And finally, I also want to thank the organizers for still organizing this conference despite current circumstances. I think this is a very nice example to show how we can continue having many conferences in the carbon-free future. So to my topic. So since this is a broad audience, I really want to start from a very fundamental question that has been the main question behind my research, which is, where do we come from? I imagine that many of us are trying to address this question, each in their own small subdiscipline. But I'm addressing this question from an extragalactic and observational perspective. To me, galaxy formation is particularly interesting because it bridges the large-scale structure of the universe, cosmology, which is really set by fundamental physics, to smaller scale in terms of, at least for astronomers, ISM physics, which controls the formation of stars and planets and so on. As I said, I'll be mostly presenting observational work, but besides observing the real universe, I also spend time analyzing or actually observing simulated universes, which is only possible for a few years, I think. And I'll try to explain why I think both of these approaches are very complementary. The main reason for that is that when we observe a galaxy, we have this major limitation that if we want to understand how galaxies form, we can observe, of course, a lot of nice individual galaxies, but it's very hard to actually see how a single galaxy evolves. It just takes too much time to actually see this, which makes testing physical theory very difficult and very different from what other disciplines in physics are doing. Luckily for galaxy formation, we are saved a bit, or we are at least helped a bit by the finite speed of light, which helps us looking back in time if we look at very distant sources, such that we can make observations of galaxy populations throughout the history of the universe. And then we can look at how different populations evolve. And by combining these sets of observations with theory, we can understand how individual galaxies evolve. This is a very famous diagram that I've already seen 10 times at least at this conference, and I guess many of you have seen this diagram as well. This is the cosmic star formation rate density that shows basically how many stars are forming every year in an average volume of the universe as a function of the age of the universe. And one very clear result that everyone agrees on is that the universe was much more active in forming stars 10 billion years ago compared to now. So we are really in this cosmic depression. But with these sets of observations, this particular one, but also evolution of galaxy sizes and stellar mass functions, and many other scaling relations, combined with insights from theory, from cosmology, gas cooling, we have now, as a community, I think, arrived at a state where we can make simulations and actually simulate galaxies, how they form in a computer. Of course, with some caveats, not all the relevant physical skills can be simulated simultaneously, but these simulations are, in my view, very powerful tools to use besides observations, because they have two major strengths which observations lack, which is that you can actually play a movie and look at how a single galaxy evolves in time, which is obvious you cannot do in observations, but simultaneously you can also observe properties that you cannot observe in simulations or observations, or that are very hard, such as dark matter content or hot gas and so on. So all this process over the years has resulted in this basic recipe of galaxy formation that I think can be summarized very nicely in this picture. This is a picture based on the Eagle simulation, but you can use another simulation or some semi-analytical model to to find the same picture. And this shows in the black line how an average galaxy, a central galaxy, roughly evolves. This picture shows the galaxy formation efficiency, which is really the ratio of the stellar mass that it assembled and now divided by the dark matter halo mass. The dark matter halo mass is the dominant component of mass and therefore sets the binding energy, and it's really important in driving many properties of galaxies. What you can see from this picture is that once galaxies started forming, they start assembling their stellar mass through star formation, somewhat through mergers. The rate at which they are forming these stars is regulated by inflows and simultaneously the feedback that's associated to this growth of stellar mass growth. I'm very broad here. I mean, there are of course many details in this picture that are not very well understood. How does this feedback work, for example? But it's quite interesting that with this broad picture we can already learn this. So at some point, once galaxies reach this characteristic mass where roughly our Milky Way is, the star formation the galaxies do not really grow in stellar mass anymore. This is often called quenching, and it's believed to be caused by the supermassive black holes that start growing exponentially in the centers of galaxies, and there's feedback associated to this growth of supermassive black holes that makes sure that further stars cannot really form because the gas is heated or expelled. And this is really the end stages, perhaps, if you think of galaxy formation. Galaxies transform into this growth mode where they actually mostly grow their supermassive black holes instead of their stellar mass. And the black hole growth is actually shown in this figure with the color coding. You can see in red that at the high mass end, the black holes start forming efficiently. So with this basic recipe in mind, what I was wondering about in my PhD is how do variations in this relation, where do these variations come from? Because you can see there's actually a lot of scattered, so on the order of factor 2 to 3, which means that an average galaxy with growth seems to be well understood, but there's still a lot of variation. And actually in the simulation, we found that at least for low mass galaxies, for star forming galaxies, this galaxy formation efficiency is strongly correlated to the halo assembly time, the dark matter halo assembly time. Maybe it doesn't sound very surprising because if a dark matter halo at fixed mass starts forming earlier, it has more time to form stars. So it will end up with a higher stellar mass if you look at a fixed time. But there's a second cause, namely that the halos that form earlier actually are more concentrated and therefore have a higher binding energy, such that the feedback may be less efficient in expelling gas. So what I think is really interesting about this is actually shown in this figure that is 15 years old. This shows dark matter halos split by their formation time. And this is a very large scale simulation of a dark matter only universe. You can see clearly that the clustering of these dark matter halos, depending on when they form, is very different. So this property of halo assembly time is really a cosmological property that is set by the initial conditions of the dark matter distribution. And but it leads to variations in stellar mass at redshift 0 at our present day. But besides leading to variations in stellar mass, it actually also leads to variations in how rapidly galaxies currently are growing. This figure tries to show that. Sometimes this figure is actually called the main sequence of galaxy formation, which may ring a bell for a few. This shows the relative growth rate of galaxies, or the specific star formation rate versus their mass. And I'm only focusing on the colored points here because the bottom right are quenched galaxies that behave slightly differently. But again, you can see that the variations in this plane on the orthogonal axis are associated to the halo assembly time. So this means really that the growth rate of a galaxy, which actually determines the relative amount of young stars to old stars, is influenced by this cosmological property of the halo assembly time, which really shows that in galaxy formation you can bridge these different scales. And the consequence of that is that, for example, in the simulation, the magnesium to iron abundance in the stars, which is sensitive to the long-term star formation history, because the alpha elements, such as magnesium, have a different origin than iron. But you can actually see that there are some variations depending on the current growth rate among galaxies. And I think it would be very nice to see if this is true observationally. And I think this is a very nice illustration of how these different scales affect each other. So for the second part, that last part, besides this very general recipe of galaxy formation, there are of course many uncertain ingredients. And one ingredient that is particularly interesting for this question on where do we come from is how galaxy formation actually started. And I've been addressing this question really from an observational and empirical perspective. And there are many questions that we can still ask and we really don't have the answer for, such as that galaxies start with ordered rotating structures, or is it really a collection, unstable collection of clumps, which obviously depends on the scale. What are the properties of the first generation of stars? How did these supermassive black holes that are really crucial in determining the fate of galaxies, how did they actually form? And what was the role of galaxies in reionizing the universe in the first gigayear of cosmic time? And this field has been really driven observationally by the capabilities of HST for almost 20 years. HST, of course, is extremely sensitive in the optical and the near infrared, has a very high resolution, which is great if you want to find distant, faint objects. There have been many people working on this, and for many galaxy candidates, a few galaxies for which distance actually was confirmed. And this all led to this picture that typical galaxies at a redshift of 7, which is roughly 500 million years after the Big Bang, and which is roughly at the end stages of cosmic reionization. So there's this basic picture that you get from the multiband photometry from HST and actually Spitzer, that these galaxies in general are very young, and they are dominated actually, particularly in the terrestrial optical, by light from emission lines instead of stellar continuum. But you can see, if you want to really understand what are the properties of these stars and what is the state of the gas, you need more than 5 data points on this SED, and you really want to get spectroscopy. Of course, the main limitation of these kind of surveys is that if you use the most sensitive telescope, HST, to find galaxies, it will be very hard to observe them, to then follow them up and get a spectrum of these galaxies. So at the beginning of my PhD, we actually tried to take a different approach and use very wide field ground-based surveys to look for distant galaxies that span a much larger field of view compared to these typical HST surveys, which allows you to find very bright galaxies. And to make this a bit easier, we combined this wide field approach with a narrowband imaging technique, which allows you to search for objects with strong emission lines. And those are nice because if by selection galaxies have strong emission lines, you can do spectroscopy more easily. But of course, it's a slightly biased sample. So one galaxy we actually found in the second month of my PhD was this galaxy Cosmos that we named Cosmos Redshift 7. This is the first image that we saw. It's really a blob in the center. We named this galaxy Cosmos Redshift 7 because it's in the Cosmos field, and the redshift is 6.6, and well, as astronomers, we can round that up to 7. But naming this, giving this galaxy this name, particularly the short version, CR7, also helped in the outreach that was associated to the press release of the discovery of this galaxy. So, for example, we did not have to worry about making nice artist impressions, such as this one. I just found this one on the internet. And actually, this news of this discovery of this galaxy, just because of the name, actually, audiences that would never, I think, read something about astronomy actually read a tiny bit of astronomy during their daily news readings, which I think was very nice. It's a slightly different version of outreach, I guess. But besides the name, this galaxy is also, I think, very interesting from a physical perspective and a scientific perspective. On the left, you can see the artist impression by ESO. On the right, you can see the HST image. That was actually made by chance. Actually, this HST image was archival because others looked at another galaxy right next to it, basically. This image shows that this galaxy contains at least 3 different components that we named A, B, and C. But what was particularly interesting that in 2015, this galaxy showed very good evidence of showing traces of the earliest stars. In particular, because when we observed this galaxy spectroscopically, we found very strong emission lines. The Lyman alpha line on the left was we knew we would find that because the galaxy was selected to have this strong Lyman alpha emission line. But besides the Lyman alpha line, which is already associated to dust poor, very young star-bursting systems, and we also saw this helium-2 emission line in the X-shooter spectrum. The signal to noise is not great, and we really would need better observations to be sure about this line. But what this line really traces is is a very hot ionizing source, because the ionization energy is 54 electron volts, which means that you need, if this is powered by stars, by a black body, you need an effective temperature of about 100 Kelvin, which is much higher than most typical O and B stars. That made this galaxy particularly interesting. Besides these detections, we did not see any metal lines that you would expect to see at typical line ratios with respect to these lines. But already, basically instantaneously, there was an issue. This galaxy was selected to be very bright. The mass is around the Milky Way mass, even though we're really early on in the history of the universe. The star formation rate is very high. And how can you get such a high mass galaxy, already 500 million years old, roughly, to contain many zero metallicity stars? That's a big problem. And the other thing is that more empirically, perhaps, is that when we look at similar objects in terms of their line luminosities, at lower redshift, later in cosmic time, these are all AGN. So the question is what is really going on in this galaxy? And the most important thing, of course, is to observe this galaxy with different instruments. And fortunately, we observed this galaxy with ALMA for, I think, 4 hours or so. So it's very sensitive ALMA observations with very good resolution. And these ALMA observations detected carbon-2 line emission, which is a coolant, actually is one of the most dominant coolants of the interstellar medium. And it detected this carbon emission basically throughout this galaxy. So almost on all these UV components, so these complexes of young stars, we see carbon-enriched ISM gas around it. So that rules out, of course, that this galaxy is really dominated by first-generation stars, at least on the resolution scales that we can see. Of course, there may be smaller pockets that are just blended with everything. So we need to get higher resolution in the future, of course. Simultaneously, we did not detect any dust continuum with ALMA, for which we were very sensitive. And this is actually inconsistent with all those lower redshift AGN that have similar luminosity. Those objects would all have been detected. So this seems to rule out an AGN origin of the strong emission lines. So this indicates really that all these different observations now indicate that this galaxy is basically a multiple merger. We see 3 complexes in the UV of young stars, and we see even 4 complexes, actually 5, in the carbon-2 in the ISM. So this is really an ongoing multiple major merger in which some very young stars are forming, which is, I think, quite nice to see. Of course, over the past years, there have been many others finding similar galaxies, less extreme galaxies, even higher redshift galaxies, even more distant. And particularly with the advent of ALMA, we are starting to probe the interstellar medium with strong emission lines in the far infrared. In some objects, we can actually map the dust continuum, try to assess how much dust formed in this very short time scale. So this is really giving us a first idea of what are the properties of the ISM and the stars in these first galaxies. And I think in the next few years, we'll hear much more about that. Just the last thing I want to show is actually we observed this galaxy last year, so after my PhD, but I'm still showing it because it's so exciting, with the MUSE GTO, with the IFU on the VLT. And this galaxy can, with this instrument, we can map out spatially resolved the spectroscopy of the Lyman alpha line around this galaxy. In this figure in the center, I show again in black contours the UVs, or the young stars, matched to the resolution of the optical instrument, the ground-based instrument. And you can see that it's really surrounded by a cloud of Lyman alpha emission, which is all the way out to 15 kiloparsec with the current surface brightness limits. And this really shows that through these Lyman alpha photons, we see that there's a gaseous envelope around these young complexes of stars. So besides seeing the ISM and the stars in these distant galaxies, we are now also seeing the gas that is likely nurturing these young star-forming clumps. So it's really nice to see a multi-scale and approach of these galaxies. Finally, what's next? This is basically how we can constrain the SED of distant galaxies now, roughly 8 data points. In the next decade, hopefully we'll improve a lot on this, in particular with the ELT, which will be extremely sensitive for the terrestrial UV part of the spectrum. This contains the information on the properties of massive stars and the winds associated to these low metallicity stars, which will be very interesting to constrain actually their properties. And of course, with James Webb, we get finally access to the red frame optical, which contains these numerous strong emission lines, which will really tell us what the ISM is doing in these galaxies. And I think what the field is really going to is from first seeing distant clumps, a few pixels of galaxies, which slowly increasing our resolution and wavelength coverage and spectral capabilities. We're starting to resolve how these galaxies really look, what are their stars, and try to answer how they really formed. That's my talk.
George, you're muted.
Okay, yeah, sorry. I understand part of my problems are probably coming from the fact that in the session information, I do not appear at all as a chair. There is only Sara. So right from the beginning, I'm in a very weird situation here. Jorryt, I have another question from Lucio, who is unable again to send a question to the system. And the first question by Lucio Mayer is supermassive black holes are, if supermassive black holes are the main quenching agent at high masses, this should happen also at very high redshift, since we know the first bright QSOs appears at Z larger than 6. How would you best look for evidence of quenching in galaxies at Z larger than 6?
Ooh, currently, that's observationally very difficult. What I would do, I mean, of course, at a very high redshift, the gas fractions are extremely high. So even though the supermassive black holes may be very active, you may have so much gas that you may still form some stars, I guess. But how I would look observationally is try to see in a spatially resolved way to see if there is some evidence for massive stars, all stars, by looking at features in the rest frame optical that trace the atmospheres of all stars. This will be very difficult because they're likely outshined by young stars and the AGN itself. I would not look at, actually, if I want to address that question, I would not look at these very high redshift quasars. I would look at moderate redshift galaxies for which we know there has been a quasar, because we could possibly measure the black hole mass, and then try to work back the star formation history of those stars.
Thank you. Sara, I do not see any of the other questions. So do you have more questions?
No other questions. Oh, yes, just now. So Oh, several, sorry, they're just appearing all now. So from Andre Felipe Ramos Padilla, I apologize if I mispronounce your name beforehand. The question is, do you think OST or SPICA will finally complete questions that ALMA and GWST cannot solve?
So one instrument was SPICA and the other one was, which one?
OST.
All right, yeah, so these instruments, of course, trace this, I think they trace this wavelength region that is basically blank in my SED. So that, yeah, definitely there's lots of features there, like the PAH features and other emission lines from the interstellar medium. So yeah, I'm pretty sure those will add complementary physical probes of the properties of these galaxies.
The next question comes from Alexander Shulevsky. Could you comment on the role of SKA that the SKA will have in studying large samples of objects like CR7, radio IR correlation studies, for example?
Yeah, so this radio IR correlation is, I think it refers to the star formation rate inferred from the infrared correlating to the radio emission. But I think, I'm not sure if SKA will have the sensitivity to detect radio emission from star formation in this particular galaxy. What will be very interesting is that SKA can map out, I think on arc-minute scales, the neutral hydrogen distribution of the intergalactic median around these galaxies. And these galaxies are predicted to be in highly ionized regions and bubbles that form at the end stages or through the reionization epoch. So around these bright galaxies, we should see holes in the H1 distribution seen by SKA. I think that would be a dream to observe.
Thank you, Jorryt. If there are any more questions, please push them now. Otherwise, we will proceed to the next speaker.
You do not have any more questions, Sara?
No, these are all the questions I have at this stage.
Okay. So I thank you very much.
No, wait. One just appeared. They just appear in bursts. A question from Chris Lintott. If the star formation rate for CR7 is 50 solar masses per year, could we think that's a limit for galaxies at C7? Or could more extreme systems be out there?
More extreme systems have been observed. There is an observation of SPT something at redshift 6.8, which is a strongly dust obscured star forming galaxy, which I think has star formation rate over a few hundred. But this is an obscured system found with that you ideally observe with instruments like ALMA. I think for an unobscured starburst, such as CR7, which you can see in the UV and in Lyman alpha light, this is probably more the limit in terms of star formation rate that you can have. If you have a higher star formation rate, you likely, I think, have already formed more dust. But more extreme systems in terms of star formation rate exist.
Thank you.
All right. That was all.
Okay,
yes,
thank
we're
you
done
very much.
with the questions.
So thanks to Jorryt for his very interesting talk. And now the third MERAC Prize is awarded to Concepción Cárdenas Vázquez in the new technology instrumental category. Concepción is from the Max Planck Institute für Astronomie in Heidelberg, but originally she's from Granada, where she has done her PhD thesis. And she got this prize for her leadership and creative work in instrumentation, from the conceptual design and the feasibility study to the final integration and verification, both in the laboratory and at the telescope, related to the instrument panic. So no panic. Concepción, you have the floor. Thank you very much.
So good afternoon, and thank you, Professor Meylan. I will share my screen first. So, can you see it?
Yes, I see.
Okay. So, in the first place, I would like to express my gratitude to Foundation MERAC and the European Astronomical Society for this prize. It is an honor for my supervisor and for me to receive it. The title of my PhD is PANIC, a wide field infrared camera for the Calar Alto Observatory. And I conducted this work in the Instituto de Astrofísica de Andalucía in Spain. My supervisor has been Julio Rodríguez Gómez. I defended it in 2018 at the University of Granada. So this is the outline of today's talk. I will give an overview of my PhD that goes from the theoretical study and optical design of the camera and its implementation and verification. I will show the performance in the laboratory and at the telescope. PANIC is a project jointly developed by the Instituto de Astrofísica de Andalucía and the Max Planck Institute for Astronomy. It is the first instrument in a program that started in 2005 to develop instrumentation for Calar Alto Observatory. EIA was responsible for the optics and software work packages and MPIA for the rest. To visualize the field of view in each telescope, here we can see it in comparison with other Calar Alto infrared cameras. When PANIC was conceived, other wide-field infrared cameras for ground-based telescopes were being developed, all of them dedicated to specific survey programs. The camera was born as a general-purpose wide-field imager, very suitable for survey types observations. So anyone with good ideas for science projects can use it, as outlined here. So let's start with the work. Next, I will give a schematic overview of the work this PhD encompasses. It has the user phases that an instrument development has, with the main objective to produce an operative instrument that meets the requirements. The project starts precisely with the collection of these requirements. So with these requirements, I produce an optical solution and a development begins. And the optical system is optimized by iteration with the performance analysis. To manufacture the system and with the detailed specification of the components, more requirements arise and have to be taken into account in the optical design. How the devices are assembled and integrated also produce more requirements that influence the optics. For the alignment, auxiliary systems have to be foreseen. They have been also specified, manufactured, etc., to be ready for the AIB phase of the instrument. The system is aligned until it fulfills the expected performance. A verification in the laboratory takes place, then providing the green light to go to the telescope. After integration and alignment of the telescopes, the system is commissioned and the instrument validated. The project timeline is organized to complete these phases described. This PhD work started just after the kickoff in 2006, when I was appointed to be responsible for the optical work package. Preliminary design review took place 1 year later, and the final design review was split in 3, being the optical one in 2008. Manufacturing, assembly, integration, and verification phase was longer in time, not only because of the difficulty to build a cryogenic instrument, but also for economical political reasons, the project was delayed. First light happened in October 2014 and followed by the commissioning at both telescopes. Everything started with the requirement collection and their breakdown. In the first stage, we have high-level requirements that will drive the optics. These are related by where the instrument will operate at the Cassegrain focus of the 2.2 meters telescope, the operation mode imaging in the infrared, including set band and narrow band filters, with the specified pixel scale to cover the maximum non-vignetted field of view that this telescope has at the Cassegrain focus, and with the appropriate detector. The detector is a Hawaii, a mosaic of 4 Hawaii 2RG that provides 4K by 4K pixels with a gap of about 150 pixels in between. The near infrared and the detector imposed to be a cryogenic instrument. A second pixel scale is required, and the camera optics solution should be a monobeam refractive with no need of a collimated stage as a result of a feasibility study of the instrument. The system specifications are related with the optical performance, such as the image quality in terms of the diameter of the 80% of the encircled energy being smaller than 2 or 3 pixels, depending on the pixel scale. And also with constraint derived from the operation of panic attached to the telescope Cassegrain focus. So a maximum weight and envelope should be observed, and those also affect the optics. Other requirements are related with the fact that this is an infrared instrument. So with the goals of having a high signal-to-noise ratio in the K-band and minimize the background, cold masks and pupil ray imager must be introduced. During the process of the optical design, more specification will be generated as the system is detailed. For example, the selection of the optical infrared materials in order to have refractive experimental data of the refractive index and coefficient of thermal expansion at cold temperatures. Or another example, the interaction with mechanics and cryogenics, the lens's geometry is affected having chamfers to use the optomechanical solution adapted for these lenses mounts. The mounts provide the proper positioning of the optics at the cryogenic temperatures. The design of PANIC and its implementation was made as follows. Based on the requirements, I produced a preliminary optical design that passed a preliminary design review. Then I produced a final optical design for a final design review that validated the system, and we can build the instrument. The optical system, the optical solution, for the optical solution, I followed these steps. The optical design approach. First, I did an approach to determine the basic optical parameters that and analyze the telescope aberrations. Then the initial optical system. I should consider then these parts: a field lens before the telescope focus to help us with the off-axis aberrations of the telescope, a field flattener before the detector because of the big field of view, and a minimum of 2 lens barrels to re-image the entrance pupil of the system in between them to be able to introduce a cool stop mask there. And to introduce in this position the filters so the angle of incidence over them is minimized, and we can have the capability of introducing narrowband filters too. The third step is the model. And taking into account all the relevant optical parameters, I modelized the initial optical system using the software CMAX. The next step is the optimization of that model, also made with CMAX, setting up the variables we can have in our system, radius of curvature, thicknesses, materials, and aiming to reach the MERAC figures, but imposing the constraint we have in our system. The evaluation. The system is evaluated to reach the MERAC figures with the constraint we have, but with margin for errors. So the final step is the error budget. An optical system is not finished until an error patchet is done. This step is essential and will help us in three ways. In the first place, to identify which elements are our worst offenders, to establish compensators in the system to relax tolerances. And in the second place, to distribute the errors for manufacturing errors and assembly alignment to make the system feasible. And in third place, to predict the system performance. This is the distribution of errors in panic final optical design, and this is the expected performance in terms of image quality. This is the optical design of the PDR, which is monobeam folded, common until the call stop, and then after that, a revolver of two barrels to interchange the pixel scale. This is the final optical design. The second pixel scale was discarded due to weight, the maximum weights in the instrument, and a pupil imaging capability was added to the requirements. So in this position, we can introduce the filters and the pupil imager lens. And to have the capability of the second pixel scale, and this was solved making that panic can work at the 3.5 meter telescope, and a dedicated cool stop mask optimized for each telescope can be introduced in this position. At this stage, deep interactions are made between the optical design and the mechanics and cryogenic. The baffling, how the different elements are nested in the optical bench, and how it will be the IRV, and where the mechanical compensators will be. In the case of panic, we have 4 compensators, 2 for distances and 2 for decentering, and they are located in the lens mount 2 and lens mount 3. Very quickly, this is the expected image quality of the final design optical model. For the 2.2 meter telescope, it was required that the diameter of the 80% of the encycler energy being smaller than 2 pixels. These are 2 pixels. And we can see here the fulfillment through the complete wavelength range along the field of view. In the 3.5 meter telescope, the requirement was smaller than 3 pixels. This is just a list of the FDR requirements and their fulfillment. And a summary of the pixel scale, field of view, and image quality expected at both telescopes. So as I said before, once the final optical design is validated, we can proceed to build the instrument. The implementation and verification of panic is organized in 3 categories: manufacturing and acceptance of the components, instrument in the laboratory, and instrument at telescope. In the first category, we have panic components and auxiliary system designed ad hoc for panic. These activities started just after the optical FDR and finished in 2012. In the panic components, we have the 9 lenses and the entrance cryostat window and the final acceptance after cryocycling. The 3 folding mirrors and the surface quality verification. The science filter set, and the pupil imager lens that also has chamfers. In the auxiliary system designed for panic, we have the following tools: auxiliary target for alignment at worm, auxiliary aluminum mirrors, also for alignment at worm, an auxiliary cryostat exit window for optomechanical axis verification at cold, a focal mask to put the detector in the optimal focus of the instrument. And I also designed a star simulator for verifying the image quality in the laboratory. The projected star here at the focus of the telescope is reimaged in the detector in these locations. In parallel to these activities, we started the activities of the second category, instrument in the laboratory. In this category, we have activities at subsystem level and at system level. At subsystem level, we started with the integration and alignment of the mirror structure, folding mirror structure, and the integration and alignment of the lenses, and the integration and of the filters and the pupil imager lens in the filter wheel. At system level, we have the adaptation of the optical system to face a configuration change in temperature for from 80 to 90 Kelvin. The feedback of the final optical design with the optical and mechanical as-built parameters to produce the as-built optical model. Next, we were able to calculate the mechanical distances for the compensators we have in the two barrels. And the adjustments in the lens barrels of the two compensators in the centering we have in lens 2 and lens 6. The optomechanical axis alignment at warm and verification at cold through the auxiliary exit window we mentioned. The complete instrument alignment at warm and verification at cold by populating the optical bench with the different elements. And this was made after 9 cryogenic cycles. And to finish the instrument integration, the final step is the adjustment of the mosaic of the detectors. And using the focal mask installed inside PANIC at the position of the telescope focus and analyzing the conjugated images of the pinholes on the detector. This was made in 4 cryogenic cycles. Finally, we did the image quality test before transportation with the star simulator, verifying that PANIC is within requirements and we were able to go to the telescope. And in the third category, after reassembly the instruments in the clean room in Calar Alto, we repeat the image quality test in the laboratory and we start the commissioning of the 2.2 meter telescope. And the alignment of PANIC was made after 3 iterations. We achieved an optimum and homogeneous image quality through the complete field of view. And this is the resulting position of the pupil imager mode, where we can see the cool stop mask in the 2.2 meter telescope, inside PANIC for the 2.2 meter telescope with respect to the primary mirror. And the 3.5 meter telescope, we did the alignments in 2 iterations. And this is again the position of the 3.5 cool stop mask with respect to the primary mirror, the 3.5 primary mirror. So to summarize the PANIC's performance, I present here the image quality in the laboratory before and after transportation. And so all the data have error bars. The measurements show that the image quality is as predicted by the as-built model, in fact, better at long wavelengths. The improvement is due to the error budget made and the compensation strategy followed during AIV. Furthermore, the optical quality is preserved after dismounting and reassembling the instrument, proving that the system is robust. Concerning the filters, this is the set installed in PANIC, the transmission curve of the operation conditions, and superposed in yellow is the sky in Calar Alto, sky transmission in Calar Alto. Good news is there is still room for 8 science filters. Regarding the PANIC's performance at the telescopes, here I summarize the values obtained during commissioning, the third column. We can compare with the expected values from the as-built optical system. We should note that pixel scale, the field of view, and the image quality match completely, and furthermore, the distortion is smaller. This is to finish. This is the first light image we took with PANIC in October 2014, where a full moon covers the complete field of view. We can also notice that 3 of the detectors suffer of degradations, especially this quadrant, bottom left, useless for science. Only this one, right bottom, is qualified for science. This is another beautiful picture we took during commissioning, the 2.2 with the good quadrant. And this is a very nice science image from Comeron et al., also with a good quadrant. And at the 3.5 to visualize the field of view, we took Jupiter, and, but also with the good quadrant. Last but not least, I would like to tell you about the detector upgrade in the very near future of PANIC. PANIC had only one problem, the detector's degradations. So the solution started 2 years ago, and the mosaic will be replaced by a monolithic Hawaii 4RG, and with no gap anymore. This is a real picture of the detector, which is already at the MPIA labs, and the cold test and the AIV in PANIC have started. This is, for example, a flat field image at cold of this detector. Since there is no change in the optics only, and we will upgrade the detector, and due to the smaller pixel size of the new detector, the new field of view will be smaller, but with higher resolution in the pixel scale. This is the new, new performance PANIC will have, the pixel scale and the field of view. So that's all from my side. Gracias. And thank you very much for your attention.
On this very well performing instrument. Are there any questions? I have no question now from Lucio Mayer. Sara, do you see any question that
Yes, there are a couple of questions.
Perfect.
So first of all, from Lei Chen, thank you for the talk. What is the bright limit of the instrument? Will a star with say K magnitude of 7 saturate the detector?
Sorry, I didn't.
I will repeat.
Yeah, thank you.
What is the bright limit of the instrument?
Yeah.
Will a star with say K magnitude of 7 saturate the detector?
So according with the science commissioning, in my notes have 21 is the magnitude, limiting magnitude for K band, G, H, and K band. Can you see me? Because I cannot.
Yes, we see you. The question was not about the faint end of the detection, but the bright end.
I don't know them.
Mm-hmm. Okay.
Because this is science.
Yeah.
I finished in the technical.
Sara, any question?
Yes, we have a question from Alexander Shilevsky. Is scatter light an issue, or was the telescope baffling sufficient to mitigate it?
So we followed a strategy to reduce the scattering inside panic. I have to summarize everything to reduce a lot of things here to read the talk. So inside the instrument, the stray light is very well taken into account to minimize it, and to block the telescope is the pupil ray imager, which we can use. So in the next phase, when we integrate panic the next time with a new detector, we have to, with the pupil imager lens, to position in the mask. I don't know if you have here, see that is not completely aligned. And so we need to move the mask inside panic to block completely the stray light coming from the telescope. Does answer your question? We can chat in the Slack.
Okay, there is another question from Matthias Fabry. Was the detector degradation expected? Will it affect panic in the future, even with the new monolithic chip?
So according with Teledyne, Teledyne is the manufacturer of these detectors, and it wasn't expected until James Webb Telescope pointed it out, because they have a lot of tests made in this Hawaii 2RG. And then we, during our IAIV, we saw the detector was degrading. And, but the new detector, the Hawaii 4RG, Teledyne says they don't guarantee, but they say they change the technology in a sense that it's very small likely that we will suffer the degradation again. So hopefully it will not degrade.
All right. At the moment, there are no more questions pushed, but we're a little ahead of schedule. So perhaps if people have questions also for the previous speakers, we could, that's an extra opportunity. And maybe George, if you want to say something more about the MERAC Prize. Go ahead.
Things, of course. And I would like first to congratulate the 3 awardees of the MERAC Prizes this year. Thank you very much for your talks, and thank you very much for ending ahead of time, which is quite nice. It leaves us the opportunity to tell to everybody that the MERAC prizes alternate. This year it was for the early, it was for the PhD thesis, and next year, nomination of this fall, it will be for the early career. So you have all the information on the website of the EAS, and I would like to recommend everybody to never hesitate to nominate people for the prizes. You can even sometimes renominate people. You know, we have one awardee per category. So if somebody is not winning a year, it may be successful the following year. And I would like also to remind everybody that there are a few prizes. There is the Tycho Brahe Prize, there is the Fritz Zwicky Prize, and the MERAC Prizes. So please discuss with your colleagues, make some publicity about these prizes, and trigger nomination or nominate people yourself. Thank you very much in advance. The more nomination, the better is actually the selection at the end. So I thank you all of you for attending this session, and I give the floor to Sara, who is going to end the chairman of this session. Thank you.
Yes, many congratulations again to the prize winners. And indeed, like George said, it's fantastic to be in a situation of having many excellent nominations to choose from. So again, don't hesitate. We really like having, you know, nominations to choose from. And most of the time, I would say all the time, we get excellent candidates, but it's great to have options. So don't hesitate and nominate people in your community. So you just got through the Q&A, you got a congratulation from the president. Roger Davis just sent you your congratulations.
Thank you.
So We're a little bit ahead of schedule, as I said, and we've been recommended not to run ahead of schedule or late. So I will give one last opportunity to ask questions to any of the speakers, including the ones that spoke before. If there's anyone who wants to say something or ask something or clarification or a question for any of the speakers, this would be your time. If not, of course, you can go on Slack, but this is the time to get a live answer. All right. Okay, it looks like this is not happening. So I will say, I will take then 1 minute, since we're ahead of schedule, to 1 minute more than I planned to present our next speaker. First of all, my name is Sara Lucatello. I'm one of the vice presidents of the European Astronomical Society. And for me, it is a great honor and a true privilege to be presenting our next speaker. She's had a stellar career of groundbreaking discoveries in astronomy. You know, she did one of the most important discoveries of the 20th century, which was still a grad student. So that's, you know, pretty high bar. She's been a tireless champion of diversity and inclusion and equity in STEM, to the point that she donated the whole amount of her special breakthrough prize for fundamental physics that she was awarded in 2018 to fund the study of women, underrepresented ethnic minorities, and refugee children to become researchers in physics. So she's been an inspiration for me personally, and most importantly for generations of younger astronomers, and probably even for the MERAC Prize winners. So Jocelyn Bell Burnell today will talk about women in astronomy worldwide. And I'll give the floor to you, Jocelyn. Thank you for accepting to speak today at the EAS annual meeting. Jocelyn, you can unmute and perhaps share your screen if you wish.
Thank you very much.
Perfect.
Sharing screen. That's not what I want to do.
At the bottom, you should see a green.
Yep, I've done that. I've lost the PowerPoint temporarily. It's there.
Okay.
Okay.
Well ahead of time. No worries.
Yep. So what happens now if I share screen? I have lost the PowerPoint. Drat. If I do share, I think I only share that, which is not what I want to do. There we are.
Yes, we see now your slide.
We see your slide. Just do slideshow and it should work.
There we go. Right.
Thank you.
So you can see the screen, you can see the cursor, and you can hear me.
Perfectly.
Thank you very much indeed. So thank you everybody and good morning. It's a very great pleasure to have this opportunity to do this talk. I've long had an interest, needless to say, on women in astronomy, and I have taken particular interest in a database that the IAU, the International Astronomical Union, has been compiling. It's been going for some time, as I will explain, and I'm looking both at the number of women in astrophysics now and how that's changed over the last 20 years. Going back to about 1990, when Derek McNally was the General Secretary of the IAU was pressed to do something about women in astronomy. And Derek McNally replied that the IAU regards itself as a body devoted to the promotion of astronomical science, and to this extent has tried not to cross the line into matters of social concern. And they deemed the status of women in astronomy to be essentially a social issue. So in 1990, in other words, the IAU was not going to touch the issue of women in astronomy or astrophysics. That changed 10 years later. Johannes Andersen from Denmark, who sadly died earlier this year, was the General Secretary of the IAU between 1997 and 2000. He was married to another astronomer, Birgitte Nordstrom, and he noted that she was having considerable trouble getting a job in astrophysics in Denmark, whereas he had no trouble at all. And he wondered if gender was an issue. He then realized that as General Secretary, he was curator of the membership lists of the IAU, including the individual membership list, and that he had information on the gender of astronomers who belonged to the IAU. And he started recording the data segregated by gender. And subsequent general secretaries have kept that up. So for the last 20 years, the IAU individual membership data is recorded with the gender of the person concerned. And it's that data that I'm talking about today. So today the IAU has about 14,000 members. There are now actually two categories, what's called individual membership, as well as membership by country, and junior membership. Junior membership is a more recent addition. So the IAU holds data recorded by country where you work, which is not quite the same as your nationality. It's the country where you work that counts. By gender, with the individual and junior categories merged, and by age. And I note incidentally that they say that only 4 people out of that 14,000 were unwilling to specify whether they were female or male. I think this is a dimension the IAU will have to pay more attention to in future, not only whether they're female or male, but whether they wish to record themselves as other or they prefer not to say. But to make my life simple, so far the recording is only by female or male. So this is the current data, very current, as of the 1st of June this year. And I'm restricting my attention to countries that have more than 200 astronomers in individual membership, so that the root N errors are not too large. And I have listed the countries here with head of the list, the country that has the highest fraction female amongst its membership, and going down from that. The world average is currently 19% female, which is not very good, it has to be said, but that's where we are. Italy is the country with the highest fraction of females amongst its membership. They have 28%. France has 26%, Brazil 23%, Spain 22%, Russian Federation 21%. And then we come to the actual average, and Netherlands is on the average with 19%. And below average are Australia 18%, USA 17%, Canada 16%, India 14%, and a group then all at 13%, includes the UK, my country, Germany, and China, Nanjing. China, Nanjing is how mainland China wishes to be described. And of these countries with large numbers of astronomers, Japan is bottom of the list with just 7% female. There are some interesting trends in this data. I see Southern European countries doing rather well for women in astronomy. Italy, France, and Spain are all in that green area of the table. South America also tends to be good, although Brazil is the only country with more than 200 members. The Russian Federation has for a long time had a tradition of women working and state nurseries provided, so it's perhaps not surprising to see it's doing very well. And I regret to note that the English-speaking countries seem to be in a block below the world average. Indeed, the UK has dropped below that block now, but it used to be firmly in that English-speaking block. And Northern European countries tend to do worse. Netherlands, of course, as I've said, is already at the world average. But Germany is down at 13%. So there are some interesting things going on here, I think. And I have to say this kind of pattern has persisted for the years that I've been looking at this data, the last 20 years. Now, you have to be nominated for membership by your country's professional body. So there is a filter, and it may be that there are more women in astrophysics in some of those countries. It's just they're not nominated for membership. Or maybe the filter works the other way. I don't know. There is the address of the website if anybody else wants to go and look at that data. So, as I've said, Southern European, Latin America tend to have higher percentage. Northern Europe and the English-speaking countries have lower percentage female. As a younger scientist, I was frequently told that women just didn't have the brains to do physics. And so I find this data comforting because it says to me it's to do with the culture in the country. It's not to do with women's brains. I'm told that there's similar global distributions for women in physics and women in mathematics, but I don't think there are bodies that record the data the way the IAU does. So I don't think there is the same quality of information there. But if it was a cultural effect, or indeed it was women's brains, then you might expect similar distributions for physics and mathematics. So what might the cultural factors be? Well, one could be that other subjects are seen as more prestigious. Maybe engineering is more prestigious than astronomy in some countries, for example. And the men would tend to be in engineering in that case, and leaving astronomy open for women. But one of the big issues still for women are childminding and domestic arrangements. In some countries, people don't move very far, so you're still living near to your parents, and parents maybe could help with the childminding, liberating you, the woman, the mother, to go and be an astronomer, at least part-time. Or maybe you live in a country where there's great disparity of income, where there are a lot of poor people, and there will be poor women who would be only too happy to be employed as your cook, your nursemaid, your laundry maid, your childminder, your housekeeper, while you, the wife, go off to work as an astronomer or astrophysicist. So there are plausible cultural factors, I believe. Now, I've been watching this data since 2016 closely. I've been watching it longer than that, but I've been monitoring the data since 2016. And I'd like now to spend a bit of time talking about how these numbers have changed since 2016. And I'm going to relax my total number criterion a little bit. I'm moving down from countries with more than 200 members and considering all countries with more than 100 members. Between 2016 and 2019, the world average of the number of females, the fraction of females in astronomy, has risen from 17% to 19%. So I consider that as a trend in the right direction, although 0.5% a year is not exactly rushing. But there's a complication, because the junior membership was introduced midway through this period in 2018. And I suspect there are rather more females at the junior membership level than at the more senior level. And this has probably partly led to the increase in female membership. So I'm not quite comparing like for like, but at least we have more women involved. The countries whose percentage female membership has risen most spectacularly in the last 4 years, well, it's our host country, Netherlands, that tops this. The Netherlands has increased the percentage of women in its contingent to the IAU from 10% to 19% in 4 years. Wonderlijk. But hey guys, how have you done it? What's the secret recipe? That's a fantastic increase. Chile has also done well. It's increased its percentage female membership from 15% to 21%. And India has increased from 9% to 14%. Those three are the countries with the biggest increases. Belgium, Germany, Italy, Mexico, South Korea, and the USA have all risen by 3%. And I regret to say the UK's done nothing. We must work on that. I've also looked at the age distribution of the membership to see if I can see the effect of junior membership coming in. This is one of the other things recorded. And I've done it in 10-year blocks, 25 to 35, 35 to 45, and so on. And I'm listing in this table the number of female members across the world and the number of male members across the world. And I give the ratio of female to male. If we look at the second column, the number of females, it peaks at the 35 to 45 age group, indeed towards the top end of that, so in the early 40s. If we look at the male membership, it peaks somewhere between the 45-55 and 55-60, so it's around about 50. The men, on average, are older than the women. So has the junior membership been responsible for the increase in members? Or is age 40 actually rather generous when we're talking about junior members? I'm not quite sure. But these two look a little bit like different populations. And I'm wondering how it's going to play out in the future. And I wonder, particularly given the current coronavirus lockdown, what changes there might be in the future. I don't know how it is in other people's countries, but certainly in Britain, with kids at home from school, it's tended to affect the mother's career more than the father's career. It's affected the amount of work the women can get through in between feeding everybody and supervising the children's schoolwork. And so we fear in Britain that the position of women in society may be reversed somewhat as a result of the lockdown. We'll see. But it will be interesting to see how various factors play out in the future. Moving back from the IAU data itself to think about other issues that might be worth remembering. I'm going to think about women in astrophysics institutes, university departments, research institutes, and so on. And in most countries, we are now enabling more women to advance up the ranks. A bit like ivy climbing up a wall. And I have a couple of pictures here of ivy. I hope you know what ivy is, but it's a creeper that will climb up the outside wall of a building. So is the advancement of women reaching higher ranks a bit like the ivy climbing up a wall? Have we enabled women better to climb up the wall? But is the wall itself any different? Are the structures that the women are now climbing up the same as they always were? And is that okay or not? I think that's a question we all need to address. our efforts have largely been on getting more women up the ivy, so to speak. But I think we also need to think, are we simply enabling them to climb a masculine structure, or is the structure gender neutral? Perceptions are beginning to change quite fast. In 1930, a British nobleman was stupid enough to write a book called The World in 2030. Don't ever attempt to predict what the world will be like in 100 years' time. It's stupid. You'll get it wrong, spectacularly wrong. Here's what the Earl of Birkenhead said about women back in 1930, looking ahead. In 2030, women will still, by their wit and charm, inspire the most able men towards heights that they could never themselves achieve. Gulp. And a couple of polls in the USA. In 1946, 65% of the USA, people in the USA, thought that men were smarter than women. But by 2018, 86% thought men and women were equally smart. So that's good signs of a change. And now with the IAU at 100 years old, we have a female president from the Netherlands, Irene van Dishoek on the right, and a female general secretary, Teresa Lago from Portugal. And that is a first and is very, very welcome. Thank you for your interest. Thank you for your attention. And I hope there is now some time for comments and questions.
Thank you very much, Jocelyn. We have a fair amount of time for questions, and you got plenty of questions. I'm going to start. I'm going to start from the first one, who's asked by Elena Maria Rossi. She's asking, even if the Netherlands is at word value, what is the fraction of Dutch female in the Netherlands? My guess is that the majority of the 19% come from South European countries. Do you know if that is true?
I don't know, and we can't gather it from the IAU data, because as I said earlier, the IAU data is gathered by the country in which you work, not your nationality. And so all nationalities working in the Netherlands are deemed to be Netherlands. I don't know how we would recover that short of a worldwide census of astronomy departments.
Which is an interesting idea, by the way, to get a worldwide
Yeah,
census.
are you volunteering?
I'm actually volunteering to do it for the EAS this year.
Right.
Not for the word, for the EAS. The next question is actually related. The next question asks, would it be possible to record the country of origin versus the country where we work to shed some more light on the situation? And I guess Jocelyn already answered that, and that would require a worldwide census, I guess.
Yes, the IAU could do it, but it would be a lot more work for everybody.
Right. The next question comes from Aurora Simeonescu. Could there be a relation between the typical salary of a female researcher compared to the average overall professions versus how many women choose to become scientists in that country? In other words, countries where astronomy pays less might have more women scientists, but that is still indicative of an underlying bias where women are encouraged to pursue lower paying jobs.
Yes, that's a lovely question and a lovely idea. Whether one could ever get the data, I'm not sure, but I strongly suspect her hunch is right. At least in Britain, one is supposed to pay the same salary to men and women, but on many markers, it's not happening, to be honest. I guess you could get median salaries for each country, something like that. I'm not sure, but that's an interesting idea. I think the hunch behind her statement that the women are tending to be found in the lower paid subjects might well be true. It would be an interesting thing to establish. What we do establish in Britain is that often the women are not paid at quite the same rate as the men, even though they're supposed to be, and in many professions, and we're trying to close that gap.
If I may make a comment on this, I think there's also the fact that for men, it's easier to migrate because of for family obligation, moving to a different country, it's easier for men. So a male astronomer from a lower paying country is more likely to have an easier time moving to a higher paying country than a woman in the same profession. So that might create also a difference because that might also be an effect. The next question comes from Cyprian Lanterman. Sorry if I mispronounced your name. Some studies show that women tend to quit the race for position at a younger age than men. Do you think recruiting tenure earlier in career would help to balance the male-female ratio?
I think one also wants to check out why it is that women are quitting the race sooner than men, which is the premise you're starting from. My hunch is that it's complications around marriage and responsibility for children that affects the careers of women more than men at the moment. Doesn't have to be, of course, except for the actual pregnancy and childbirth. But I think society's still a bit skewed that way. Interesting thought. Yeah, don't know.
The next question comes from Connie Ertz. And she says, it's more of a comment than a question. She said, I would like some strong women like you, Jocelyn and Edwina, demand from our journals to build up their statistics and how the submission acceptance of paper is different from male and female-led first authors since the COVID lockdown. In other fields of exact sciences, these data are being analyzed. I think we owe it to our field to monitor this.
That's really interesting. Pre-COVID, we know that in the United States, they've done a lot now of refereeing of, for instance, Hubble telescope proposals with a double-blind system, and it's markedly increased the fraction of women that are getting time. Or sorry, it's largely increasing the fraction of time that goes to women, PIs. So yeah, I think anonymity is very, very important. Just how you would, whether there's enough data for COVID and immediately pre-COVID lockdown, I wonder. You could probably do it for submission rates. That might be the easiest way. I'm thinking as I talk, as you can gather, but it's a really interesting question, Connie. Yeah, I think looking at submission rates and submission rates of grant proposals or other funding proposals would be really, really interesting over the next, well, for about the 12 months from the beginning of lockdown, would be an interesting database.
The next question comes from Cressida Cleland. Part of the solution involves a large cultural shift, e.g. changing young children's idea of a scientist and allowing young girls to feel represented. How long do you think this might take? More than a few decades?
Yeah, it's different in different countries, I think. I'm guessing slightly, but I think it is. One of the campaigns I belong to in Britain is a campaign called Let Toys Be Toys, children's toys. I don't know how it is in other people's countries, but toy shops in Britain are color-coded. There are things packaged in blue for boys and things packaged in pink for girls. And there's a strong disincentive to go and buy a toy from the other half of the shop because it's very obvious you've picked up the wrong packaging. And the toys packaged pink are Little Princess and cookery sets and things like that, whereas the boys' toys are, I think, much more interesting. You know, things like construction kits. In Britain, children are gendered very, very, very early. Indeed, there's even a suggestion that mothers handle new babies differently depending on whether they're boy or girl. That the boy babies get handled more robustly, shall we say, and the girls are treated like something very fragile. I'd be interested to know what happens in other countries. Do children also get gendered very early? And if they do get gendered, what's the message sent to the girls? Is it all little princess or Barbie or things like that? It's insidious, and it's quite a campaign to get it changed.
The next question comes from Nicole Nevzadba. Apologies again for me pronouncing your name. You often hear today that the problem is not only one of women's contribution to STEM and astronomy, but a problem of minorities in general. Do you think that women should be treated like other minorities, or is this a danger by playing out different groups of victims of a masculine environment? How should we respond to such statements?
I think I'd be inclined to say that actually women are probably in the majority in a country, because generally speaking, nature provides slightly more female than male in order to achieve successful breeding. So I think I would not go down that route that's suggested to begin with, that women are a minority. I think that's starting from, strategically, that's starting from a point of weakness.
Okay.
Does that make sense? You sound a little dubious, Sarah.
No, sorry, I think my connection just died for 1 second, so I was not sure what was happening. Thank you. Thank you. No, that's not what I meant. The next question or comment comes from Johan Knappen. First of all, he says, thank you for this inspiring talk. Your availability of poor people to help at home argument seems strange. Astronomy salaries in countries like Italy or Spain are not high enough to allow women in astronomy to take much advantage of low-paid labor. And the Netherlands hasn't suddenly been flooded by cheap labor in the last few years. I think education, young age outreach and policy, positive policy, and resistance to change, in negative terms, are much more important. That's his comment.
Yes, I certainly would agree with you in Europe, Johan. I think that's true. But I once asked a Mexican woman astronomer why there were so many women in astronomy in Mexico, and she gave me a one-word answer: maids.
Yeah.
Maids.
Chile and Argentina too, probably.
Yeah, I think it will vary from country to country, to be, or even continent to continent, to be absolutely fair. Yeah. But yes, Johan, in the more affluent countries, fair comment.
So there is a comment actually about the number of women in the Netherlands by Ralph Viers, and says, Viers, sorry. He said that there was a definite big push targeted in universities targeted to increasing the number of women. So that perhaps answers your question about how they did that.
But it's good to know that there is targeting and it can work.
Yes, yes, I agree. That's amazing.
Yeah. Good.
So from Carol Jackson, whilst it's important to know the origin of women working in other countries, I think it's an important fact to see which countries appoint women to senior positions. Yeah. Isn't this also a major factor to seeing where the underlying biases exist?
Yes, I think that is fair comment. Although any woman in a country will be, her career progression will be affected by the conventions in that country, regardless of where she comes from originally. So her progress will depend on which country she's in. Her being there in the first place may well depend on which country she comes from. I agree.
So we're going to have 2 more questions because it's kind of late. I'm going to ask one now. In Italy, the salary in astronomy is the same for men and women. However, women tend to take longer to rise to higher positions, which are also paid less. At PhD level, the number of women is somewhat higher than men. So I guess it is a matter of helping women stay in the field in the earlier career years and help them being promoted? This question comes from Anna Walter.
Yeah, that's interesting data. I guess it's how the women get through the childbearing years, child rearing years is one big factor, and how the household reconciles husband's job progression with wife's job's progression. You know, if it involves moving to another part of the country and maybe the spouse losing their job, what do the family do? What do the couple do? It's not trivial. There are coupled data points here.
Mm-hmm. The next question comes from Claire Worley. What are your thoughts on anecdotal evidence of the research of women being less cited and in some cases completely ignored by groups dominated by men, thus holding back the science and so the career prospects of women?
I think probably there is a tendency to be more aware of the work by your own gender, assuming it's in your field. And so that probably affects the citation. And certainly I suspect there's some kindred feeling amongst women. I can't help noticing, for instance, how many of this session's questions have come from women. I think that's probably unusual in this EAS meeting.
Yes.
So, yeah, it would be great if we just cited papers because of their quality, wouldn't it?
But there's so many factors that influence how we see things. It's incredible.
Yeah, yeah. And you know, if you're like me, you have some kindred feeling towards women researchers and you try quietly to, you know, promote those.
Understood. I'm going to ask one last question and then all the extra questions, because we're running late, all the extra question and the discussion can move to our Slack channel, where I really hope that Jocelyn can join us. Because it's very active and you'll get many more questions for sure, and many more opportunities to answer them. So the next question is that from Hannah Calcutt. How can we ensure female, especially junior researchers, have an equal voice at conferences in terms of disseminating the research and asking questions?
Yeah, that's really important. I think we should be regularly monitoring who gets to ask a question after a talk at a conference. I don't know to what extent this is done, but of course, if there's, you know, 45 men and 2 women in the room, the women perhaps are a little put off asking a question. But yeah, and also facilitate women getting to meet the speakers and that kind of thing as well. There's still plenty we can do. But in the longer run, we're going to have to broaden this from just women to other aspects of humanity. It's not, gender's not just black and white or male and female. So there's other issues that maybe we can pick up and sweep along with this one as well.
Indeed. So thank you very much, Jocelyn, for your inspiring and illuminating talk. And I hope you can join us in the discussion in the Slack. I will move all the unanswered questions there if people want to keep on answering or discussing them in the plenary session channel. Thank you to all the speakers for the plenary session. This has been extremely interesting and very well attended, I may add. Let's move to the lunch sessions now, or to the Slack. Goodbye, everyone, and thank you.
Thank you.
Thank you, everyone. Goodbye.
Bye. Bye. See you.
All right.
Bye-bye.